Alright, so the next part is, rather than heating, we will use this solar panel to actually generate electricity directly. PV panel, photovoltaic panels. Okay, I guess this is a picture that show kind of like they're trying to show the future. So here's a nuclear power plant on the background, but they opt basically to use PV panels. And that's what happened in Germany. So in Germany, basically, after the Fukushima accident in Japan, when it happened in Germany, they panicked and they said, we are not gonna use nuclear energy anymore in Germany. And that's weird because in Germany they don't have natural gas, they don't have oil. They basically, without nuclear energy, what else can they do? So they either has to import natural gas from Russia, or they can use the sun and the wind. And so in that year, they were the largest country in the world to install PV panels on the roof. And that was weird because their flux, the density radiation in Germany is similar to Alaska. So they don't get that much sun actually. Okay. So first of all, the efficiency of photovoltaic panel. This is the x-axis is the year, starting from 1975, all the way to what, 2015, 16, and those curves go all the way up, right? But you can see that the maximum in the lab, hit what, 40% or something. That is the maximum in the lab. Very expensive ones. This is like maybe the one in the International Space Station. They can afford to do this. But so the efficiency is like, you can see for a lot of design, it's like 20% efficiency. But again, for all renewable energy, it's not really the efficiency, it is the dollar per kilowatt hour that matters. Okay? So yeah, 20%, and so what? 80% of the sun is not gonna turn into electricity. Well, right now, 100% of the sun is just falling on the parking lot and it's not doing anything. So I mean, if you give me 20%, that's not bad, right? So how does it work? How does those PV panel work? So this is mainly electrical engineering, but as a mechanical engineer, let's just get the main idea so that we understand why the efficiency is that low. Okay, so there are electrons and there are basically the neutron and protons inside, right? Those electrons are hanging around the atom, and if you have electron in the conduction band, so this conductor is an insulator. Insulator basically get the electron intact, basically. They are all stuck, and that's why if you are touching an electric wire with a device that has electric insulator, you don't get the shocked. Why? Because that current does not go through them. Okay, and the reason why the current does not go through them is because they are stuck to their atom. So there's conductor, there's insulator, and there is something called in between, semiconductor. So those semiconductor, their electrons are waiting for the right energy, and if you give them the right energy, they start flowing electrons. Okay, so the amount of energy that you need to give the electron to that he can start flowing, it's called the gap energy. Okay, and so that gap energy, if you give him that gap energy, he will turn into conductor. And so the idea here is that we will give the electrons the gap energy by photons, the incident radiation from the sun. Those photons will get absorbed, and according to quantum mechanics, every photon can get absorbed by one electron. You cannot split the energy. I cannot just like throw $20 on you and everyone can get $1. No, it's like every gift needs to go to exactly one student. So every photon has to go exactly on one electron. And so if that photon's energy is not enough to jump that gap, it doesn't matter how many is flowing. He will not generate current. And if that energy is higher than the gap energy, the electron will jump a little bit higher, but then he will dissipate that energy and start flowing. So meaning that you really have to have exactly the right amount of energy for that electron to to go through, and anything more is lost energy, and that's why the efficiency suffer. And anything less, you cannot multiply them. You cannot just say, just get a little bit energy and wait for the next photon is coming. No, he can't. Alright? So the semiconductor are, the most famous is silicon and those guys, gallium and those things. And so what happened is they are sitting in a lattice like this, right? And if you give them the right energy, the electron will start flowing. But wouldn't it be nice if we have extra electron already available? So that it's easier for him to flow. And they do this by something called doping. So what doping is that rather than pure crystal like this, all silicon, they dope it with other element that have extra electron. And on the other side, because this electron need to go, when we flow them, they need, like in a battery, where does the electron go? They go from one side to the other, right? And in the process, they go through the lamp and turn the light for you, or go through the cell phone and make the thing work. But the electron need to go from one side to the other. So what they do in this doping thing is, so this is, I'm explaining the gap over here, and the magic number is 3 electrovolt. Electrovolt is some kind of energy unit. It's like joule. We'll see the conversion in a minute. But it's energy. And so above 3, then it's like really hard to move electrons because it takes a lot of energy. That's an insulator. Less than this, that is basically a semiconductor. Conductor is like, no, get my electron here. Here you go. Right? So the doping is such that when they do doping is that they can make the crystal with other impurities that will have extra electron. And on the other side, they dope it with element that will have less electrons. So they call it a hole. So when you have extra electron, that's basically one type, and when you have less electron, that is a hole. And so now you put those two material next to each other and you created a junction. And that junction basically have electrons extra on one side and electron missing on the other side. And it's just waiting for the light to fall. And when the light fall, those electrons will start flowing. Okay? And you would probably think, but do I even need the sun? If I just make them touch each other, wouldn't the electron leak and fill the holes and we are done and I don't have any extra electrons? And no, it doesn't work this way, because if those electrons, so notice that every atom is balanced already, right? We have extra electron compared to the neighbors. But when that electron go over here, he made this place which was already balanced. It became negatively charged. And when he left his place, he left in the atom a proton that now have extra positive charge. So what I'm trying to say is that, yes, when you connect them, there will be some that will leak, but immediately you will create an insulating layer that basically say you cannot cross anymore. This place is too much. We have too much electrons now. You cannot come to us. Yes, we originally have a lot of holes, but we were neutral. Now with you guys coming toward us, now we are negatively charged. So any more electron tetrite will come, it's just too much. You have to have energy to be able to cross that place. And so they actually don't cross from that place, they go from the other side when you give them the light. And they go through your load. So the battery does not just eat itself, or that junction does not eat itself. The junction will generate electron that will go through the circuit. Okay? So over here, he's trying to figure out, so how much energy, what is the wavelength that it takes for the silicon to move his electrons, right? And so there is this equation that basically say, depending on the wavelength of the light, you can calculate the energy. So how much energy we need for silicon? 3 electrovolt, right? Not 3 electrovolt. We need, I'll show you the gap energy for the electron. for the silicon. But the equation is E is hc over lambda, all right? And c is the speed of light, 300,000 kilometer, and lambda is the wavelength in micrometer, and h is Planck's constant. And so using this, you'll be able to calculate the convergence. So for silicon, it takes 1.11 electrovolt. That is the gap energy for silicon. So now what is the wavelength that will do this for you? Lambda hc over E, and you can see the conversion between electrovolt and joules over here. And so you do this, and lambda is 1.12 micrometer. So anything that has 1.12 micrometer or shorter. So short wavelengths actually have more energies than long. Okay? So the longer the wavelengths, the less energy it is. So 1.12 or higher, 1.12 or shorter wavelengths will have enough energy to dislodge electrons in the silicon. Okay? So he's saying that if the wavelength is higher than 1.12, there will be no photovoltaic effect in silicon. This light will just go through. That's why they say silicon is actually transparent for infrared. So if you have a silicon plate in front of your eye and you can see in infrared because you are working for the Navy and you have like infrared Google, you will see through it. You can see through silicon because that wavelength just goes through silicon. Okay? So the reason how people can build more and more efficient solar PV panel is, can you guess? What is why those are so high? Those purple one, if we read them, multi-junction cell. Okay, so with multi-junction cell, you can cover all the wavelengths that exist in the light, and basically you don't leave anything untapped. So he's saying silicon is 1.11, okay, and then any other wavelengths, it will be useless for him. The rest of the light will just go through. But then if you make all those material, you can start harvesting different wavelengths. But some of those material are expensive, adding them is too much, right? But that's basically how people can improve the efficiency. So this graph is showing you, here is the wavelengths, wavelengths in micron, and if the sunlight has basically energy more than this, for silicon it's say 1.12 is here. So anything shorter than 1.12, that is a lot of energy, right? But it's wasted. It's wasted on silicon. Why? Again, because we said that if the photon comes with more energy than it needed, it'll just go away. It get dissipated. And anything longer wavelengths than this, all that long tail of the sun radiation is wasted. It does not even go through silicon, right? So that's why. Okay. So what would you do with this then? If you are faced with this problem, and like might look at all that energy that's basically got wasted on us. People use it for heating. So they would combine the photovoltaic, and behind it they will harvest the heating. Just the low grade flux. The flux that's not able to generate electrons, but it can be used to heat, right? So they will combine both of them. Okay, very good. So he's basically over here say, as you add more and more materials to the junction, you will be able to improve your efficiency from like 30 all the way to higher and higher. But you have to add more and more junction that harvest all the different wavelengths. Okay. So this was the physical background. Okay. As far as we are concerned as mechanical engineer, that PV panel is basically two junctions next to each other, and when the light comes through them, we get electrons out of them. They are basically a battery. They are a battery that start working when you hit the sun. You hit it with the sun, then it will start working, and it will have a voltage, right? And we will calculate that voltage that will come from, and unfortunately, or nature of thing is the voltage is not that high, and that's why they need to stack them in parallel or in series. They need to stack them in series to increase the voltage, right? So 1.5 plus 1.5 plus 1.5 plus 1.5, then you can end up getting like 24 volt panel for your system, right? And they stack them in parallel to get more power, right? Or more current. So you add the current, right? So that's how we, so some of the problem will be how many cells we need to arrange, like how much by how much. The number of in series has to do with the voltage, and the number in parallel has to do with, do we need to 300 watt panel or do we want 120 panel? That's basically will tell you how much it is. Alright? So the PN, positive negative junction, right? We said that you create negative type and positive type. The negative type will have a lot of electrons, and the positive type will have a lot of hole. Okay? And that layer would get stuck after a while, after like just free will leak. After those electrons will start coming over here, they will leave positive charge behind them, and that prevents more electron to leave that place. And when they go to the positive type, they will create negative sign on them, and that prevents more electron again from crossing. So they stop flowing this way, and instead they will basically go here. So the electron that will get popped up by the radiation will just go to the load and come back. Alright? So they would model it like this. They would say, well, here is the cell, and that cell will generate current that basically go to the load. That's the J load. So J is like the current but per unit area. Okay? And by the way, when you see those solar panels, usually they are blue, right? And they are thin. So this, the top part is one, like the positive side, and the bottom side is the negative side, for example. So the battery is basically that tile, the top and the bottom. Okay? And when they connect them in series, they connect the top of one to the bottom of the other one, right? Connect the positive to the negative and the positive to the negative. So they don't just connect all the positive together. That would be in, they do this would become in parallel. But in series, you have to go from the bottom to the top, the bottom to the top. So J is the density. So it's the current per unit area. The current leaving per unit area. J load. And J, this guy is the one that goes through the junction. Okay? So the electron generated, some of them will go through the junction. You don't want that, right? Go through the junction. And the other that get generated in the cell will end up going to the load. Right? And so the load current density is basically whatever generated by the sun minus whatever will escape through the junction. Make sense? Some will escape through the junction, we don't benefit from it, and the other will actually go through the load. So they calculate the junction load by basically, or current by this, and you can see it's function of the temperature. That's why you want to cool them, and it's function of the voltage. That's why you don't want the voltage to be that high, otherwise a lot will escape, right? So at the end of the day, this equation for GL over GS, the density, current density become like this. Okay, sorry, become like this. Okay, so meaning that it will be a lot of current, and then once you increase the voltage of the load above 0.6, no electrons will go to the load. Why? Because the voltage is so high, it's easier for the electron to just go skip through the junction. right? Why would I go to this big load on me? I just can skip to the other side. The gap in the middle is not strong enough compared to this. So that 0.6 is, they call it the open circuit voltage. Okay, and the maximum current is the short circuit current. This is if we forget the load and just connect the battery together, short the battery. So this is the maximum current, this is the maximum voltage. If we run here, yes, maximum current but zero voltage. Power output is zero. Run over here, yes, maximum voltage but zero current. Power output is zero. So what do we really care about is the I times the V, and that is this. Okay, this curve. This curve is the power output. And so where do you want to work? You want to work here. What is that point called? The point of maximum power. And the current and the voltage corresponding to that point is the voltage at the maximum power and the current at the maximum power. Okay, very good. So you wish this curve was almost a rectangle. That would be ideal, huh? If that curve was really a rectangular, then we would run here. We would run at the point of maximum power that corresponds to the maximum voltage and the maximum current, but it's not. And that curve, how far it is from this perfect rectangle, huh? There's a number for this, the F, basically how close you are to the perfect rectangle. Okay, so what are we going to do in this chapter? Because this is clear electrical engineering. We are users. So you being a mechanical engineer does not prevent you from using the cell phone. I mean, you don't really know what is how does the circuits work, but you are very good at using your cell phone. So we should be very good at picking the right PV panel from Home Depot or Lowe's and figure out exactly how many we need to meet our heating or cooling or whatever load we are running in our place. That's what we are supposed to do. Okay, so the difficulty that we will have is that the sticker that come on the PV panel, when it say 300 watt or 200 watt or 120 watt, that sticker is guaranteed to generate that power only if you had this PV panel in the lab where they measured the 300 watt under one sun illumination. Okay, and that is not going to happen in Tulsa, Oklahoma. We are not going to have 1000 watt per meter square. So our job is to pick that sticker that says 300 watt and turn it into what will actually happen in any day, at any month, in any city that we want. So I'm going to finish by this, that the output out of this PV panel is function of how much incident radiation is coming. Makes sense? Depending on how many photons you are sending, the current will determine. So we will modify the output of the panel by this ratio of what? Of the one sun, which is 1000 per meter square, 1000 watt per meter square, and what's actually going to happen on the roof of your house. So if we know what's the incident radiation on the house and it turned out to be 800 watt per meter square, we will use that number to convert the sticker to the actual power. Okay, and we'll finish here by now. Thank you.